Hello, everyone. We're going to get started working on solutions where we left off. So we had talked about a couple different ways that you can describe a solution's concentration. We've got mass percent, volume percent, mass volume percent, and then the big one that we use a lot, molarity, which is moles over liters. Just want to touch on this real quickly, this thing called ion concentration. So when you have a material that is dissolved in water, if it's composed of ions, it'll break apart into those ions. And you can actually figure out how many moles of a certain ion you would have in solution based off of the chemical formula. So if we look at let's look at something that isn't ionic. Let's look at something that's molecular, because a molecular compound usually reflects the concentration of the solute. So if I have 1 molar glucose, this compound here, molecular, it's not going to break apart into ions. So when I have 1 molar glucose, the solution will contain 1 mole of the glucose for every 1 liter of solution, right? That's what molarity is, moles per liter. Now, let's say we look at this ion down here, or this ionic compound here, which is 1 molar CaCl2. So I know that when this thing gets put into solution, I'm going to end up with a calcium ion, and I'm actually going to end up with 2 chlorine ions. So for every 1 molar solution, it will contain 1 mole of CaCl2 per liter, but it's going to contain 2 moles of the Cl- per liter. Why? Because the formula tells us we get 2 for every 1 molecule. If I was to write something like FeCl3, and we were to drop that, we would assume that a 1 molar FeCl3 solution would have 1 mole of Fe and 3 moles of the chlorine. So determine the molar concentrations of sodium and then the phosphate ion. The phosphate ion we're going to keep as a whole. Of a 1.50 molar Na3PO4 solution. So when looking at this, I should get 3 of these and 1 of these. Right? 3 sodiums in every molecule and 1 phosphorus in every molecule, or phosphate in every molecule. So what we're going to really do is you just take whatever the molarity is. So if it's 1, it's easy. You just take, it's whatever the subscript is. But if we have something more than 1, in this case, we have 1.5 or something less than 1, we take whatever that is, the molarity, and we just multiply it by that factor of how many we get. So if the molarity of the sodium will be 3 times the 1.50 or 4.50 molarity concentration. Or we get 4.5 moles of sodium for every 1 liter. The molarity of the phosphate, because there's only 1 of them, it's going to have the same concentration of the overall. So in order to calculate the concentration of the individual ion, you take whatever the initial concentration was, and you just multiply it by whatever the subscript is. It's pretty easy. So let's say you have a 2.5 molar K2CO3 compound. I want to know what is the molarity of the K plus and what is the molarity of the CO3 2 minus. Okay, so give me these. It shouldn't take too long. For the K plus, I can see off the formula that I'm going to get 2 Ks for every one of the compounds. So I need to take my 2.5 and multiply it by 2 for a total of a 5 molar. As far as the CO3, there's only one of those. So I'm just going to take my 2.5 and multiply it by 1 to give me 2.5. Pretty easy. All right, so in a lab setting, there's usually these things called stock solutions that are like in the back room, and they're highly concentrated solutions. And the instructors will use, or chemists or whatever will use the stock solution to make more diluted solutions. You would never actually really use the stock solutions. They're kind of too highly concentrated. So many lab procedures will call for less concentrated solutions that we just get from that stock solution. It's much more practical to have one concentrated stock solution than to have like every concentration possible. You know, do you have 6, 5, 4, 3, 2, 1 molar stock solutions? No, you just have the 6 and you dilute when you need. So how do we dilute? Well, there's a really easy equation because molarity equals moles over liter. We can actually put it into this equation, which says M1 V1 equals M2 V2. And sometimes you'll see this written as C1 V1 equals C2 V2. Here, the M is standing for molarity. Here, the C is standing for concentration. You can use either one. Okay. We could use a variety of concentrations. You could do mass percent, mass volume percent. You can plug those into this as well. They just have to be in the same units on both sides. So M1 V1 equals M2 V2. M1 is the initial, or this is going to be related to the concentrated solution. So this is the stock solution. M2 is the final. This is your diluted solution. So M1 V1 equals M2 V2. There are 1, 2, 3, and 4 variables. So you'll be given 3 of the 4. You'll solve for the 4th. This equation works because molarity multiplied by volume gives you the number of moles of the solute, which should be the same. This equation does not apply to solution stoichiometry. So we will talk about solution stoichiometry a little bit later. That is a much more complicated process. This only applies to diluting. When the problem says, hey, you have this solution and you're diluting it, you can use M1 V1 equals M2 V2. Safety note, when diluting acids, always add acid to water. I remember that by acid to water, safe as an otter. Okay, so here's an equation, or here's an example of a problem. It says prepare a 5 liter of a 1.5 molar KCl solution from a 12 molar stock solution. So the problem is asking you how much of, I mean, it doesn't say explicitly here, but it wants to know how much of that concentrated stock solution do you need to make this final amount. So we know what we want our final volume to be, our V2, we want it to be 5 liters. We know what we want our final concentration to be. We want it to be 1.50 molarity. And we have a stock solution in the back that's a 12 molar solution. So we need to decide, well, how much of this initial stock solution do I need to pour out in order to dilute it? So we need V1. We got M1 V1 equals M2 V2. We're going to solve for V1. V1 equals M2 times V2 over M1. And we literally, it's just as simple as plugging everything in. So we take our M2, we plug it in here. Our V2 goes here and we divide it by our initial molarity. we end up with a value of 0.625 liters. So what you would need to do is you would need to take out or measure out 0.625 liters of this 12 molar stock solution and dilute it down to 5 liters, and that would give you exactly this concentration. So here they are, they're taking, first they're adding the 0.625 liters of the concentrated stock solution, then they add the water, and then they dilute. So we're not going to do solution stoichiometry just yet. We are going to do it, but I want to give you another M1V1 problem. I guess I was using that. Okay, what is the final concentration if 6 liters of, not if 6 liters of a 12 molar HCl solution is diluted to 150 liters? So go ahead and set that up using your solution dilution equation, find your M1s and your V1s, your M2s and your V2s, figure out what to solve for. Okay, so a pretty simple equation in that we just need to use M1 V1 equals M2 V2. So our M1 is our initial concentration, which we said was 12 molar, specifically hydrochloric acid. Our initial volume is 6.0 liters. We don't know what our final concentration is. That's usually not how it works in like a lab setting. You wouldn't just like dilute and see what the concentration would be. Usually you're trying to dilute to a specific concentration, but for the sake of the problem, we're looking for that final concentration. We know the final volume is 150 liters. So if we've got this equation, we want to solve this guy. So I need to move V2 to the other side. V2. So my M1 is my 12 molar. I'm going to multiply that by my V1, which is 6.0 liters. I'm going to divide it by 150 liters. So what we're doing is we're seeing how many times are we diluting, and then we use that factor and multiply it by our initial concentration. So the factor that your volume goes down or up by is the same factor that your concentration will go down by. They're proportional to each other. So we get our 12 times our 6 divided by our 150, and we get a new concentration of 0.48 molarity. Any questions on that? Because I'm not going to go over a second one just because it's pretty simple unless there's like a specific question on where something's coming from. Okay, so this is for solution dilution. I used to have an instructor back because my degree is in environmental geochemistry. So I did a lot of work in geology, and I used to have an instructor back in my undergrad who would say, the solution to pollution is dilution. I was like, no, that's horrible. I mean, it's true in some ways, but we should not all be walking around thinking the solution to pollution is dilution. Okay, so let's move to solution stoichiometry. Wah, wah. So remember stoichiometry from a while ago, where we went from grams of one thing into moles, and then we were able to convert it into moles of another thing, and then back into grams, and we could use a balanced chemical equation to do so. So in reactions where we're dealing with aqueous reactants and products, it's a lot of times it's more convenient to specify the amount of the reactants in terms of their volume and their concentration. So instead of giving like, oh, I have 55 grams of hydrochloric acid, I would say something like, oh, I have 55 milliliters of a 5 molar solution. We can use the volume and the concentration to calculate the number of moles. And if we can calculate the number of moles and we have a balanced equation, we can jump around that equation moles to moles, right? So I'm going to go back and write the flow chart that we had used a while ago, which was grams of A can get us into moles of A, and moles of A into moles of B, moles of B back into grams of B. Now in the center here, this is where we use the balanced equation. Here we use molar mass of A, molar mass of A. Here we use molar mass of B. Now I'm going to add to this flow chart another limb. So from here, I'm going to pull it off here, and I'm going to say volume of A. So instead of being given something about the grams, I could be given something about the volume. And let's remember, what does molarity equal? Molarity equals moles over liters. So if I have my molarity and I have my liters, I can figure out moles. So this is where we use, in order to convert, we use molarity of A. If we have the volume, we can use molarity of A and to get us into moles of A. If we have moles of A, then we can get into moles of whatever compound B we're looking for. And then I could hop back into volume of compound B. Again, in order to do that, I would use molarity of B. I'm actually going to add another limb here. We could be given the molarity of A. And to get to moles, we could use the volume of A. And we could be asked for the molarity of B. And in order to get that, we would use the volume of B. Okay, so if we were going from volume to moles, we use molarity. If we're going from molarity to moles, we use volume. That's the flip-flop because it's all from the same equation. So this will start here with this kind of limb of the flow chart. So here is the same thing that you guys already have written out. Volume of A can convert into moles of A, which can convert into moles of B, which can give us volume B. A and B are two different substances involved in the reaction, and the conversion factors between them come from the stoichiometric relationship. So that's how we hop. So if we look at this problem here, okay, we've got a balanced equation. How much of a 0.125 molar NaOH solution do we need to completely neutralize 0.225 liters of a 0.175 molar H2SO4 solution? So first of all, you got to ask yourself, how do I even know that I need to be doing solution stoichiometry? Because it's not always going to be written at the top. Well, if you see a balanced equation, you're probably going to be doing stoichiometry. If you see within the problem, do you see how it's asking or it's giving you information about one thing and it's asking about another thing? There's two different compounds here. When it's asking about information on two different compounds, that means it wants you to hop from one thing to another thing within the balanced equation. That's stoichiometry. So I'm actually going to copy this over because I kind of solve these problems not totally different, but I just go a little bit more into my setup. So let's bring this over here. You're not going to let me paste, are you? Okay, how much? Sorry, give me just another minute here. Copy this equation over. Okay, so H2SO4 plus 2NaOH gives us Na2SO4 plus 2H2O. Okay, so here is a solution stoichiometry problem. Now, we're talking, I like to look at what they're referring to. We're talking about this thing and this thing. All right, so those are the two things that I'm going to play around with. These things I'm not really going to look at. It's not that they're not important. They are the products and they affect how the equation is balanced. But for this problem, I'm just sort of not going to look at those. So I'm going to decide what is compound A and compound B. So compound A is going to be whatever I have more information on. Okay, so the thing that I have 2 pieces of information on, that'll help give you a place of where you're going to start. So in this one, I have 2 pieces of information off of H2SO4. So I'm going to say compound A is H2SO4 for this problem. I know its volume. And in this case, it is 0.225 liters. If that wasn't in liter, if it was in milliliters, convert it to liters. Okay, when we're doing these problems, we want that in liters. The second thing I've got is its concentration, right? So I know that its molarity is equal to 0.175 big M. Now, this, for solution stoichiometry, because we're going to be using dimensional analysis, it's not really useful to have it written as 1 unit. So I'm actually going to change this to its mole per liter unit, 0.175 moles of specifically the H2SO4 in every 1 liter of solution. So when you've got this, figure out what compound A is, get your volume into liters, and take your molarity and just convert it into moles per liter. It's the same numbers, you just put it as mole per liter. Now let's figure out what compound B is. Okay, compound B is the other thing. Compound B is going to be what you have less information on and what you're trying to solve something for. So NaOH, we only have 1 piece of information and it says how much. So we're trying to figure out the volume. So do I know the volume? No, that's what I'm looking for. Do I know the concentration? I do know the concentration. So the concentration for B is 0.125 big M. Again, I don't like it for dimensional analysis being a single unit. So I'm going to change this to a mole per liter. 0.125, and it's specifically moles of NaOH for every 1 liter of this solution. Are you with me so far as just how to organize the information? As you get better at these, you may not have to do all of this, but I do feel like it helps to kind of lay it out. So what did we say as far as our flow chart was concerned? This problem is going to get really long here. But we said that we're going to go from volume A into moles of A, into moles of B, and then we can hop back into volume B. Filling in, I need molarity of A for this. I need the coefficients from the balanced equation here, and then I need molarity of B for this. Do I have all these pieces of information? I do, actually. I have everything and it's all laid out. So let's start with the first step, which is just write down what volume A is. So volume of compound A is this 0.225 liters. So I'm going to write that out. 0.225 liters, and I'm going to add H2SO4 because we're talking about A. So if I want to go from volume of A into moles of A, I need to use the molarity of A as a conversion factor. Now, I've already, because of this setup here, I've already done that, right? Here is my conversion factor. I want liter to be on the bottom and I want mole to be on the top because I'm trying to get away from volume and into moles. So the way that this is written is perfect. We can just plug that right in, which tells us that, I keep forgetting the number, 0.175. Okay, so we get 0.175 moles of the H2SO4 in every 1 liter of the solution, of the H2SO4 solution. What happens to the liter for this first step? They'll cancel. Okay, so we've done this. We've used molarity to get from volume into moles. Now that I'm in moles of H2SO4, this is where I get to use the coefficients to go from A to B. So A is the H2SO4, B is NaOH, And then we just need to see what the relationship was between those two from the equation. So look, 1 mole of this will yield 2 moles of this. So I'm going to put a 1 with the H2SO4. I'm going to put a 2 with the NaOH, specifically moles, sorry. So 1 mole of this will yield 2 moles of this. That gets rid of moles of A. And now we're into the B side, which is good. We're getting closer to what we want. The final thing is to get to our volume of B. And in order to do that, we need to use the molarity of B. So I need to use this thing here. Do I want to put it in just like that? Well, what is dimensional analysis all about? It's always about canceling units, right? So if I want volume, I want to put liters on top. And if I want to get rid of moles, I want to put the mole on the bottom. So I'm going to actually flip-flop this conversion factor. The 1 liter will go on the top. The 0.125 moles will go on the bottom. And that will leave me with this canceling out. So at the end of the day, and this is liters of NaOH, I will end up with a unit of liter of NaOH. So we take everything that's on the top and we multiply it, and we divide by anything that's substantial on the bottom that isn't a 1. And we end up, let me just plug and chug. I know it's on the slides, but so we're multiplying it. Okay, and I get a new volume of 0.63 liters, specifically of the NaOH solution. Fun, isn't it? So I would go through all the steps. We're going to do more practice. We're going to do at least one of these. But I want you to go through the steps. I'll give you a problem that's pretty similar to this. And I want you to mirror it. So figure out the compound A, get the volume, get the molarity in a dimensional analysis conversion, figure out compound B, move through the flow chart and cancel units as you can. Okay, so try and just replicate this process right now. So let's say we've got, what do I want to do? I want to use my brain and it is just not accessible right now. Okay, so how don't copy just yet. Let me write it out because I've got to kind of think about what I want to say. How many liters of a 1.5 molar HCl solution are needed to neutralize 16 liters of a 8 molar NaOH. Okay, yes. How many liters of a 1.5 molar HCl solution are needed to neutralize 16 liters of an 8, and let me make it at 8.0 so we have some significant figures, 8.0 molar NaOH solution. And I'll give you the balanced equation. It's just our simple neutralization. Hydrochloric acid plus sodium hydroxide will produce water and the salt, which is NaCl. And it's actually balanced just like that, 1 to 1. Okay, so I'm gonna give you all about 6 minutes, as much time as it takes me to go brew my coffee. So about 6 minutes. Follow step by step what we did in the last problem. All right, figure out your compound A and B, adjust information if needed, and then plug into that flow chart. Hey there. So hopefully I didn't completely lose you by leaving you out there to work on that. But at least you were able to decipher which compound is compound A and compound B. The thing that we have more information on for this problem is the NaOH. So I'm going to go with compound A as NaOH. We know its volume. So the volume is 16 liters, and we don't need to convert it because we want it in liters. If it happens, sometimes they give you these problems and they'll give it to you in milliliters. Make sure you get into liters. It'll throw your magnitude off. We have our molarity. So the molarity is 8.0 big M. Again, I don't want to use this. I want it to be as a conversion factor. So 8.0 moles of NaOH in every 1 liter of the NaOH solution. Compound B is the other guy. So in this case, it is HCl. We don't know its volume. So just like the last problem, we're kind of trying to solve for volume. We do know its concentration. The concentration is 1.5 molar HCl. Again, I'm going to right off the bat just change that to 1.5 moles of HCl for every 1 liter of HCl solution. I'm going to stop there. Does anybody have any questions on that? On where I got all that information from, on why I changed things, so on and so on. Just throw your mute off if you do. Okay, so I'm going to write out the flow chart, which is volume of A is going to convert to moles of A, and that will convert to moles of B, which will in turn convert back to volume of B, because I'm starting here and I'm sort of ending here. So let's write our volume A. It's 16 liters of NaOH. How do I get from volume A to moles of A? Off of that master flow chart, we use the molarity. So I'm going to use this thing right here. And I like how it's set up this way with the liter on the bottom and the mole on the top. So now that we're in moles of compound A or the NaOH, I want to get into moles of compound B. Well, here's the equation. We're looking at this thing related to this thing. It's a 1-to-1 relationship. So 1 mole of NaOH will yield 1 mole of HCl. Is it always 1-to-1? No, the last problem we did wasn't a 1-to-1, it was a 1-to-2. So don't always assume 1-to-1. Last step is to go from moles of B into volume of B, and we use the molarity. Now, again, here's the molarity, but I don't like it set up like this. I want to flip it. I want to put the liter on the top and the mole on the bottom because mole is here and I want to get rid of the mole. Okay, so the 1.5 moles of HCl are going to go on the bottom, and that's for every 1 liter of HCl. Check that all the things cancel as you move along, and then you just plug it in. So we take our 16 times 8, and really we just divide it by 1.5. And we get a pretty large number, which to me makes sense because this is a very high concentration and this is a relatively low concentration. So if I'm going to neutralize it, I'm going to need a lot of this to neutralize that. So I got a volume of 85 liters of HCl. How do you guys feel about that? If you go through the steps, it's not too bad, right? There are instances though, where instead of, where was that? It'll give you the same setup, but instead of solving for volume A, it wants you to find the final concentration. And so in order to do that, we'll actually have to use the volume of B to do it. So I will show you guys how to, we'll do one together. Getting super cramped. Okay. So what concentration of, we'll just stick with NaOH and HCl. What concentration of NaOH is needed? Or hold on, give me a second to write it out. So what concentration? What is? Not what concentration. What is the concentration of NaOH if 350 milliliters? Let me reread it, make sure it makes sense. So what is the concentration of NaOH if 350 milliliters of it neutralizes 280 milliliters of a 2.5 molar HCl solution? Okay, yes. So that is our problem. I'm gonna walk you guys, or I'll walk you through part of this. So write that out. And then I want you just for right now, just take a minute to tell me what compound A is and what information you have on it. What's compound B? And make sure you convert things into the units that we like for dimensional analysis. Okay, so what do we have more information on? What do we have less information on? And then from there. And the equation will be the same. It's hydrochloric acid plus NaOH gives us H2O and NaCl. Okay, so compound A for this problem should be the hydrochloric acid because we know two things about it. We know its volume, and the volume for this is 280 milliliters. Now, because we're doing dimensional analysis with molarity, which is in a unit of mole per liter, we want to get that right out of milliliter into liter. So it should be 0.280 liters of HCl. We know the concentration of this thing. Its molarity is 2.5 big M of HCl. Again, I don't really like it written like that, so I am going to change it to 2.5 moles of HCl in every 1 liter of the HCl solution. Compound B, we know the volume. Volume is equal to 350 milliliters. Again, I'm just going to convert that right into liters. So 0.350 liters. And we want to find molarity. So for this problem, we can work it a little bit different in that I'm going to write what the equation is for molarity. Molarity equals moles over liters, right? Specifically, if we're looking for the molarity of B, it's going to be the moles of B over the liters of B. Do we have liters of this thing? We actually already have that. So this is the number here that's going to get plugged into the denominator. If you want to, you can even just plug it in right now. We can say, hey, moles of B divided by 0.350 liters is going to give us our molarity. So when we're going through our dimensional analysis, we can stop once we've hit the number of moles of B. We can just stop there, or we kind of get to stop at the third step instead of going all the way through. So if you see here, volume of A converted into moles of A, converted into moles of B, and then we were kind of going converted into volume of B, but we actually get to just, we don't have to do that last step. We get to stop right here when we get to volume B. When we get volume B, then we just thread that into the equation. Okay, so let's set that up. Actually, I'm going to have you set that up because you should be able to get to that point. All right, so get from your volume of A into moles of B. And then once you've gotten that number, I want you to thread it into your molarity equation. I'll give you 2 minutes for that. That setup, the first setup, should be similar to the last two problems we did. Okay, so this part here is similar to what we did with the other problems. We take our volume of A, which is 0.280 liters. And we're going to use our molarity to convert it. So I like how this is set up. That's good. So 2.5 moles of the HCl for every 1 liter of HCl. And we'll cancel the liters. So that gets me from here to here. Then I want to go into moles, which is the coefficients. Now off of the balanced equation, again, this is a pretty basic one. It's a 1-to-1 ratio. So 1 mole of HCl will yield 1 mole of the NaOH. I never even explicitly said that this was NaOH, sorry. Compound B is NaOH. So the moles there will cancel. So we'll be left, and we can just stop there. That's where we stop for this specific problem to give us the moles. So 0.280 multiplied by 2.5, that's really it. So I get a value of 0.7 or 0.70 moles of NaOH. I'm not quite done because I want to solve for molarity. So I need to take this number here and again, fish it into this equation here. So let's remove mole of B and actually put what the mole of B is. So the mole of B for this is 0.70 moles. Moles divided by liter always will yield a molarity. So we'll divide that by the 0.350. And we get a molarity of dun, 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 2. Or to give it some significance, 2.0. Big molarity, NaOH. Questions with that? I think this is one of the most mathematically complicated things that we do in the semester. Okay, so that's why I'm like really specific about kind of laying everything out. Questions? No, yes. No, okay. We actually will do a little bit more practice of this in the next chapter because the next chapter is all on acids and bases, where we neutralize an acid and a base, and this is pretty much a neutralization problem. So we will revisit this in the next chapter and we'll do like 1 or 2 more. But as far as, you know, hopefully the setup is making sense going through here, and hopefully you're kind of seeing why it's important to really lay everything out. Okay. The last bit of this chapter gets into freezing points and molality. We're not going to do any of this. All right. So just by, yeah, all this. Boiling point elevation, antifreeze, osmosis. No, we're not doing any of that. Okay. So that's where we'll stop. We'll stop at solution stoichiometry. So we are done for today. You guys have one more chapter, just the acids and bases chapter, and then we'll be like finishing up. Then it'll just be tests and review and final. So if you have any questions or you want me to go over another thing, I mean, we've got another like 12 minutes or so on the clock. Otherwise, you're free to go. If you have personal questions, hang around and I would have no problem helping you out. Otherwise, enjoy your weekend and make sure you're getting on top of the homework and the quizzes and all that stuff so we can just get as many points as we can before the semester's done. Bye, everybody. Melissa, do you have a question?